Good afternoon, everyone. Welcome to the post-lunch session of this workshop. And this session has two lectures. And the first lecture is a tutorial lecture, and it will be given by Professor Manish Jain from ISC Bangalore Physics Department. And the topic of this lecture is GWBSC method. So, please.
Okay, good afternoon, everyone. Welcome back to the post-lunch session. I will try my level best not to get you all to sleep after this very nice and sumptuous lunch this very nice hospitality and very nice lunch. So we'll start off from where we had left off, and what we had talked about in the morning. Let me just briefly recapitulate what we had talked about in the morning. What I had done is I had shown you. So I hope I had motivated you why we should learn GW. That's what the first thing that I did. Then I told you about that to get quasi-particle energies, the quantity that you need are the poles of the Green's function, right? And the way to calculate the poles of the Green's function is to calculate by the self energy. And then for the self energy, we are going to calculate. We are going to take the first diagram in the expansion in the string Coulomb interaction. And I told you that which is the GW method, and I told you that the W here is the dynamical screen potential, and it is analogous to the Hartree clock, where it is just the IGV, which is the Baire exchange in terms of the Baire exchange, right? And then we talked about how we should do these calculations to begin with, and what I said is that in principle you can solve the Kohn-Sham equation, which is what we often do as the starting point for all of these calculations. And once you have the Kohn-Sham equation, you actually solve these equations. And now what you do is you assume that the quasi-particle wave function is the same as the Kohn-Sham wave function. And if you do that, basically you see that these things are already taken care of. All these three terms are the same. And essentially all that is different between the two equations is that one contains this complicated object related to the self energy, and the other had this VXC, which you already built in. So you actually do a first order perturbation with sigma minus VXC, right? That's basically what we had. That's where we had stopped. Okay. So now let's go on a little bit further and things, and then of course I told you a little bit about how the calculation is done, which is what I called as the best G, best W approach. And I'll come back to why we call it the best G, best W approach, or as people call it, the G naught, W naught approach, right? That is what this approach refers to. And essentially, to just give a little bit more detail, you start with this DFT equation, and then you have to construct what is called as the irreducible polarizability, the chi naught, right? And this is nothing but your RPA expression for the polarizability. So IgG, right? Then once you have this, you actually construct the W, right, by solving a Dyson-like equation. And once you have that, you have the W, you have the G, you can construct sigma, and then do this. Now let me. So this is all very good in principle, right? This is all done, and I've done, and maybe I don't need to give this lecture. But the problem is that when you actually start running a code, there is a lot of complications and a lot of different details that one needs to actually understand when one is running this kind of a GW calculation. So what I thought is, in this hour and 15 minutes or so, I will sort of give you a flavor for what are the various other things that you need to understand to actually run this calculation. Because when you in the tutorial section, you guys are going to run the calculation, and you run something, you're going to get out something, right? That of course, unless you get naans and papadam, as I call it, right? You get something, right? But the question is, what do you make sense of? What numbers should you look for? What is what, and how is it? How to make sense of all of this is what I'm going to try and tell you. So the first quantity that you actually need once you have done the DFT is you need to calculate the static polarizability or the irreducible polarizability, which is chi naught, which I said is nothing but I G naught G naught, right? So what you can do is you can actually, if you think about this this matrix of G, if you just think about it for a second, you will realize that the dimension of this matrix, just like the Hamiltonian matrix, is size G, and there's another size G, right? That is, it's a G by G matrix, Ng by Ng. Ng is the number of G vectors, right? By the way, you're all familiar with the plane wave basis, and are you guys all familiar with that, or are you not familiar with that? I should back up and ask that question first. Are you guys familiar with plane wave basis? I mean, you can always do this not in a plane wave basis, but it's typically done. What I'm going to talk about is done in a plane wave basis. So, are you all familiar with that? Yes, no, maybe. Yes. Okay. That was a partial yes, and I'll take it as a firm yes because that suits me. So if there's somebody who wants me to really explain it, I can do that. But okay. So the idea is the following. So if you write the expression if you write IgG and you write out what is it that you need to calculate, you need to calculate the susceptibility, this irreducible polarizability. This is chi naught. So you need to calculate, this is a matrix, and it has to be calculated for every Q. Okay. And the way it works is, if you look at the expression for this, okay, it actually has two matrix elements in the numerator and an energy denominator. Okay. So you write two Green's functions, right? And you say that I'm going to sandwich this in plane waves. So I can see that I have lost a lot of people. So let me spend a little bit of time and say what exactly am I doing here. I have this chi naught, right? Formally, this is all fine. Now I want to write a matrix for this chi naught, right? Which means I need to write both of these in terms of matrices, right? I mean, that's one way to do it. Or I want to write the matrix element of this chi naught in a G prime. So I have, on one side I have a G, at the other side I have a G prime. K plus G, Q plus G, and Q plus G prime, right? So I want to find out that matrix element. So if I write that matrix element, and if I put in the expression for the Green's function, something like this, I will essentially get two matrix elements in the numerator. Because there'll be one from an integral over R, and the other will be an integral over R prime. Okay? And essentially what I have to do is actually have to calculate these matrix elements. Okay? Now, typically the way, and when these are just nothing but my Kohn-Sham eigenstates. So I have done a Kohn-Sham calculation for the band structure in a solid. But at every k point, I have a whole bunch of eigenstates. Okay. Now I have to calculate this matrix element for every pair of eigenstates that I want. So I pick a Q. So let's say I pick a Q and I pick some Q. So for that Q, I know which k and which k are connected. Right. The moment I know which k and which k are connected, I am supposed to calculate this matrix element. The standard way in which this is done. And this is actually a very nice mathematical trick that you can use to calculate this. So normally what you write this out as, it will be written as an integral of, right? There will be u n of k plus q. So let me just write it out now that I take it. So you will have an integral u n So now this one also has a phase which is e to the minus I, k plus q dot r, and this one has a phase e to the I k dot r. Right. So the q's and the k's are all going to cancel out. Only it will basically turn out to be just an integral over u. What? Oh, it's flipped around. I don't think I can write backwards. Okay, that's good. So that is this is the integral that you have to calculate. This is dr. Okay, these UNs are the same as what Jain was talking about in his talk. These are exactly the same UNs. Okay? So what happens then is that instead of calculating, so what you can do is if you look at it, if you stare at it long enough, these are all self-periodic functions, right? UNs are self-periodic functions. That's what he talked about in his lecture, right? So essentially, what you can do is start here. So, sorry, okay, this is start. That's okay. So the thing is, if I consider the product of these as a density, right? There's some density, some rho that I can define with the product of these two wave functions. Then it is just the Fourier component of that product. It's just the Fourier transform of that in real space. Does that make sense to everybody or not? Some rho of n k plus q n prime k of r, right, which is defined as the product of these two, e to the I g dot r. Right? Yes, no, maybe. Yes. So then essentially what I can do is I can take the product in real space and just do the Fourier transform and I have the answer for all g's in one. And that is typically what is done in all DFT and in all all of these calculations where you need these matrix elements because you have to calculate this for every g. You have to calculate this for a large number of g's. And if you try to do it one by one, then it is for every g it is an order n process, and if you have to do for n g's, then that is an n square process. Whereas if you do it by a Fourier transform, you know that it is n log n. So you drop down the scaling by one order by one factor.
So this when it is matrix.
Yeah, it's just the product of these two. Real space UN K cubes. Just the product. Okay. So the question then becomes how, where do you terminate this? And the way you terminate this is you define a new cutoff. You just say that, okay, look, in principle, I'm supposed to do this for all whatever I had my cutoff in my calculation, my plane wave matrix elements up to which I took. But in principle, you can actually define a new cutoff, which we call as the screen Coulomb or the dielectric energy cutoff or the screen Coulomb cutoff. So for all g's less g and g primes less than this, we are going to compute, that is the matrix size that is going to be. And for all q's, we are going to calculate this. And remember, in principle, this has to be frequency dependent. There should be an omega here and there should be an omega minus term over here, which I'm not writing, right? So we will take care of that in a minute. There's another factor here which you have to keep in mind is that this sum is over, in principle, over all unoccupied bands. Because the Green's function, when you started out, was not just over occupied states, it was over all states. Right? And if your Green's function is over all states, when you do the matrix element, that is going to show up. There's no way to avoid that. Right? So there is a convergence parameter where you have to actually converge this with respect to the number of unoccupied states. And herein you should start seeing the difficulty in doing GW calculations, which is that not only, unlike DFT, which only depended on the occupied states, because the quantity of interest here is the Green's function, involves the Green's function, you actually have sums over all empty bands in your calculation. Okay, in principle, you cannot do all empty bands. Nobody can. Nobody does that. But you have to cut it off in some way, and it has to be such that you have to make sure that this cutoff over epsilon and this cutoff up to which energy you go, they have to be roughly the same. There's some reason you can find out that if you don't do that, if you do things, if you take very few bands in one and cut off very large, then you get you can get very long.
But aren't you saved by the denominator?
So the denominator, unfortunately, doesn't save you as much. You would think that's a very good point. You would think that this should cut it off, right? Because it is going as 1 over the energy, right? But what happens is that it does. In fact, it should. In fact, if I think of the screening for very large genes, right, it should be bare. So this matrix should go to identity. which it does, right, goes to infinity very slow with the number of empty states that you have. And that's really the problem. Now, there is, of course, a way around all of this, which is that you can say, I don't want to calculate it in this way, but I can do some DFT, some linear response in DFT, right? I mean, I can do Sternheimer equation to actually get this quantity. You guys did you learn about? So, you know, you can actually take a system and you can perturb it, right? Just like you do phonons, right? What do you do in phonons? Did you guys discuss phonons or phonons? No. A bit about phonons. Okay, so the idea is, if I perturb a system, right, I can calculate its response, right, with using density functional perturbation theory, right? Just like I have normal perturbation theory, I have density functional version of it, right? So similarly, you can actually perturb the system with the appropriate potential and calculate the response to that perturbation, right? And you know, using using a linear response kind of formalism. But typically, you know, this is the simplest way of doing things, or if you want, you know, this is the most common way of doing things, wherein you actually calculate the response by just a sum over states. You just plug in the Green's function in that expression and calculate the matrix. Okay. So and it doesn't converge very slowly. It converges very slowly with the G and G prime. So it becomes diagonally dominant, right? But it doesn't go down to 1, or in this case 0, because the identity is going to be added separately. It doesn't go down as fast as you want, and that sort of makes some difference. Okay, so once you have this object, right? Remember, the object that we are interested in is not chi naught. We are interested in W, right? So what you do is, from that object, from that chi naught, you actually construct epsilon, not epsilon inverse. This is epsilon. Then you invert this matrix, right? That's what the code does. So you see that the code will actually take this matrix, it will invert it. Okay? This is called chi naught. This is epsilon, and then it will invert it, and then you multiply it with V, and you will get the epsilon inverse V, which is the W, that's the quantity that we're interested in. Here, if you think about in terms of what is needed to do this calculation, you just need the eigenstates and the eigenenergies. That's all you need from DFT. Right? Once you have that, you can construct this. How high you go over here is up to you. Right? In principle, you have to converge it. Right? How many Q points you're going to do is also up to you. But then, if you choose a Q, you have to have states at K and K plus Q. So you have to have a grid which is compatible with that. So all of this becomes, you know, a big mess. It's not complicated physics-wise, but computationally it's a mess. You have to keep track of different grids, and we will talk about that when we do the tutorial in more detail. Okay. So once you have this, you actually have the screen-Coulomb interaction, right? And in principle, now all you have to do is multiply this with the Green's function, and you have your self-energy, right? Except, if you look here, we actually never constructed the Green's function. Funnily enough, it's a GW method where, you know, we say G is the Green's function, W is the screen-Coulomb interaction. So the way that we're going to do the calculation is we are never going to actually ever construct the Green's function. It's GW without the G. So, right? But you know, the point is, maybe the next part can also be done without actually ever constructing the Green's function, and I'll show you what happens if you try to do the matrix elements of the Green's function. If you, for example, you know, what we are interested in is not the self energy per se, even though I wrote it down as, you know, you can write the self energy down, right? What we are really interested in, if you go back here, is really this matrix element of the self energy. Psi DFT, sigma, psi DFT. That's the matrix element that we really want. Right? If you gave me the self energy, the full self energy matrix, I would still have to compute this, because that's the only object I know how to use. Right? So instead, what you do is you go back here and you say, okay, if I take the screen exchange and the Coulomb whole term, and if I, you know, try to calculate the matrix elements of these, what will I get? Now I've written this in a slightly general way. What I said to you is that both these have to be the same bands, and an n prime have to be the same. But in principle, you know, you can write it as the full matrix and diagonalize that matrix, whoever wants. So in the static limit of the GW, yeah. Yeah. Both Q and K are in reciprocal space. They are essentially the same. So,
Whatever plane waves.
so no, it's not plane waves. So K is basically the crystal momentum at which you did the calculation, right? Now, if I've done the calculation at a bunch of crystal momenta, right? If I perturb the system, where does the response come? So let's say I'm sitting at one K point, and at that K point I add a perturbation. Right? The perturbation actually goes everywhere in Brillouin's law, right? That everywhere is characterized by this. There's another K, if you wish. I call it a Q, right? But just to, otherwise I would have a K prime and then it just complicates my life because I also have K prime in my equation. Yeah? Does that make sense? Right, the Green's function, the product that I wanted was in real space, right? If I Fourier transform, I'll have two indices in some sense. So when I do the products, there will be some things which will be summed over and some not. And basically, there's a chi of Q and K. Chi will be only a function of Q because K's will all be summed over. Right. So you know, these expressions all look horrendous, right? They are very big, and post lunch, you know, they are looking even more sleep-inducing, if you wish. But you know, there's no way around it, unfortunately. The central thing that you notice over here is that throughout the calculation, right, you need matrix elements. Right, these are the same matrix elements that I will show you in several different forms. Okay? The matrix element, as I said, is defined as KQG, where you have basically just taken this object and calculated. It's just this object that I've just talked about. It's characterized by three numbers: the K, Q, and the G, right? And N and N prime. So which batch states are you actually going to set? So the same kind of things show up for all of these expressions. Okay? And I have shown you the static limit because the static limit expressions are simple. Okay. If you look at the expressions for the full, the full frequency ones or the generalized plasma pole ones, I would need 2 slides to actually write all of them down. But essentially, all that is being done is just this. And all the quantity that you need, you already have this. This is the W, epsilon inverse V, that you already have. You just need a whole bunch of matrix elements again over here and sums over them in some way to actually get the full calculation. So if you think about where you started from, you did a DFT calculation, eigenvalues and eigenfunctions on the entire grid. That's all you need for the entire calculation. Right? Once you have that, you have everything. Sorry? The U and K's are the self-periodic part of the wave function, right? The side, right? So we have the eigenvalues and eigenfunctions. That is these are the eigenfunctions. Yeah. 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 So in the static limit, you can actually play another trick, which is actually a very nice trick, which is that in principle you needed a sum over all states, right? But in the static limit, when you take the limit of omega tending to going to 0, exactly equal to 0, because something happens with the denominator, which I will not get into. Basically, it becomes identity. It becomes the completeness relation. So you can drop one of these, the sum completely out of your expression, right? This was n prime, n double prime n, n double prime n prime. But when you write it out, essentially what happens is this summation becomes identity and it drops out. Okay, and it becomes a very, very nice and clean expression. I say this becomes a very nice and clean expression because when you look at the GPP expressions, the generalized plasma bond, which I'll talk about in the next slide, it actually involves a sum over all bands, even over here. So you had previously a sum over all bands for calculating the polarizability, right? That's what I had shown previously. There's a sum over all empty states, which you will cut off. Even over here, you actually have a sum over all empty states. In this particular case, it drops out, so you know the exact answer. because I can analytically sum over all empty states and write the answer. This is not true for any of the other expressions. So if this is all there is, then what is this generalized plasma fold? Why do we worry about the generalized plasma fold and so on? So the argument is the following. See, in principle, what we were supposed to do. Let me see if I can find. The self energy was actually a function of energy. The self energy was actually a function of frequency, right, or energy, right? So the Green's function is a function of energy. The screen Coulomb interaction is also a function of energy, right? Because your dielectric function actually depends on energy. Yes, no? Yeah, I think I've lost most of the most of the course. Okay, so just believe me that it is a function of energy. Okay, this is actually a product in time. If you understand many body language, you can actually understand that this is just a product in time. So in frequency, it is actually a convolution that you're supposed to do. Okay, and the problem is that computing this for all frequencies is very expensive. It's not very expensive, but you need to store it and you need to do a whole bunch of things. It actually causes a lot of problems. So instead, what you do is you make the following observation, which is that the imaginary part of the epsilon inverse for any q is actually a very peak function. Okay. Now, this is something that you've all seen in your condensed matter 1 course or in your solid state, right? Which is you've actually seen in the Drude model that there is a plasmon frequency, right? And essentially at the plasmon frequency, your epsilon 2 is peaked and so on and so forth. That you've all seen, right? It's basically an extension of that idea. It's really just an extension of that idea. That the imaginary part of the Green's function of the epsilon inverse is actually a peak function. So what people came up with is that, okay, let's not compute it out at all frequencies, because we'll have to store it, we'll have to deal with it, we'll have to do a whole bunch of things with it. Instead, let's write it in some approximate fashion, and then try to determine what these constants are, and then we can do the integral analytic. The problem with this is, you want an ab initio method. Right? What I just said is words, sounds all very good and well, till you actually start saying, okay, now I have to do this. What should I pick my A to be? Right? What do I pick my omega to be? I need a way of coming up with what T and omega are, and it has to be an ab initio way of coming up with this. And so essentially, what you can do is if you take this and you do the Kramer-Kronig, to go to the real part, at omega equal to 0, based on this, you can actually find out what the answer is going to be. Right? You have calculated what the value of this has to be at omega equal to 0. This is what you calculated because we did polarizability at omega equal to 0. This you already know. And then there are some rules that this epsilon inverse has to satisfy. And you can see that the plasmon frequency sort of shows up. So bottom line is that at the end of the day, you need an ab initio method, a method where you don't put in anything from outside to find out what the parameters are, right? This thing can be made ab initio completely. You don't have to give something from outside for you to figure out what the parameters A and omega tilde are, right? Once that is the case, then you're all done. You can make this approximation and you can find out what the answer corresponding to this is. And if this approximation is any good, your answer will be close to the reality. If it is bad, then your answer will not be close to reality, right? And because we have made the observation that it actually is peaked, you assuming it a delta function should probably not be so bad, because you anyway were going to integrate over all the frequencies, and it turns out it is not such a bad approximation, and that's what is very commonly used in all of them. We're not home free yet. If you thought this was bad enough, yeah, it's an interesting thing. So the point is the following: if what we're supposed to do is calculate the quasi-particle energy, right? If you remember, the quasi-particle energy was the eigenvalue, but the self energy also depended on the quasi-particle. Right? So just like in DFT, where your Hamiltonian depends on the density, and you have to solve the Hamiltonian to get the density, right? To get this eigenstates and get the density. It's the same thing. Your eigenstates, your self-energy operator depends on the energy, the quasi-particle energy, and the eigenstate is also the eigenenergy is the quasi-particle. So you actually have to solve this equation self-consistent. Okay, so how do we do that? So normally what we do is as I already said, in principle you can write it in terms of the entire, you don't have to write the first order correction. You can write it in terms of all the DFT eigenstates, right? You'll get a matrix and you can try to, put some value E in and see what the answer comes out and then go back and, plot it as a function of E and then figure out what the solution will be. That's what you should do. That's what nobody does, okay? Because it's very expensive to do that. So what you do is you have already made this approximation that quasi-particle energy is this approximation I've already shown. So what you assume is that the self-energy is actually linear in energy. The self-energy depends on energy as well, right? So you assume that the self-energy is linear in energy. And if that is the case, then the only quantity that you need is the del sigma del E. Because that is the slope of that self-energy. You calculate it at 2 points, calculate the slope, and then solve this, quasi-particle, linearize this, and then figure out what the correct solution is. Once you linearize the quasi-particle. But actually, if you think about this for a little bit more, you realize that this del sigma del E object is actually a physical object. So in the morning when I was showing you the spectral function, I showed you this, this quasi-particle peak, and I showed you the satellites, and we had a whole bunch of questions around that. And I said something about, in this first peak, you actually don't get the entire spectrum. You don't get the whole weight, right? That number is less than 1. This del sigma del E is actually related to this quasi-particle renormalization factor. So you can show that this is actually physically relevant, and this is what is. What it tells you is how good of a quasi-particle do you really have. We're assuming that when you kick an electron out, the object that exists in the system, in this Fermi liquid sense, is actually a quasi-particle. It's a particle which behaves like an electron, right? Because unlike a hole, right? It's one object that behaves like a hole, right? If on the other hand it doesn't, then it becomes very tricky to think of it in that way. And this sort of tells you a little bit about how much spectral weight is inside that. And that gives you a sense of whether your quasi-particle approximation by itself was valid. So now I get back to my what is this best G best W thing. So the idea is, as you saw, there's a whole bunch of things that we did to get to this point, right? And you can actually start saying that, look, you did this, you did that. How do you know this is correct or not? And the answer is, I don't. I mean, a priori you don't, right? I mean, you do this, and this is what you get. And if you remove that approximation, that's the only way to test whether this actually was good to begin with or not, right? Or you compare it to experiment. But there are so many tuning parameters that you can stop at the appropriate time, which is never a good idea. But so what I'm trying to say is, the best way to check whether you are actually whether you made the approximation that you made, whether they were good or bad, is to remove that approximation and see what the answer you got. So it turns out what I described as the best G best W approach of the G naught W naught method, where we started out with the DFT G and the DFT W, right? And we did the eigenvalue self-consistently. Now you can say that, look, you put in the eigenvalue in the when you did the self-consistency, you got a new quasi-particle eigenvalue. Shouldn't you be updating your Green's function with this? And shouldn't you be updating your W with this new eigenvalue? After all, you had a mean field eigenvalue and you had a mean field eigenfunction. You got a new eigenvalue, shouldn't you update the self-consistent? And that's where this whole business of self-consistent GW comes in. And there are at least four flavors. There are at least 4 flavors, and depending on and you will see that people will do various levels of self-consistency depending on what gives them roughly the right answer. Actually, there's no other way to say it. So you can say that I have a new eigenvalue and I'm going to only replace it in the G. I have a new eigenvalue and I will replace it both in the G and W. I have a new eigenvalue and I could do it, I could flip it around as well, not replace it in the G and do it in the W. Or I can say, I will find an optimal non-local static exchange correlation potential to actually figure out how to mix and so on and so forth. So, or in principle, what I should really be doing is doing everything completely self-consistent. My eigenfunction should be determined self-consistently, my eigenvalue should be determined self-consistently, and everything, that is what I should be really doing. And so on. There are many, many more flavors to all of this. Okay. It used to be that people would mostly only do G0 W0 approximation and would report only numbers for G0 W0. But I think increasingly you will find as you look at the literature, there are more and more of these kinds of things that people also do. It's becoming a murky business in some sense, right? Now, you update this, you don't update that, you do this, you don't do that, and but okay, that's if there are often very good reasons for updating one thing and not the other. For example, how many of you have run DFT calculation for germanium? Priya, I know, has run, but any of the students, have you ever run germanium? NDA germanium? You should try to do that. Okay, you have run. What do you get a metal? Have you ever, germanium is a semiconductor, right? You've been taught that in your coursework, right? Have you ever run germanium in DFT? You should do that. You will find that it becomes a metal. So now you have a problem. The system that you started out with was a metal, and in principle, it is supposed to become a semiconductor, right? If this theory is any good.
If I remember, PP.
Yeah. Even I think in some versions of NDA you will also get a metal. If you use something fancier, you will not. That's correct. But now let's say you're doing DFT and you do germanium, you get a metal, right? And you calculate screening for metal. Now, screening for metal is different from the screening from an insulator, right? You understand that, right? In a metal, the epsilon inverse are supposed to diverge in a certain way, and all these kinds of things are supposed to happen. Whereas an insulator, it behaves differently. So now what should I do? I mean, I can run this whole program, but then what should I do, right? I mean, I got a metal and it should become an insulator, and that's not a real metal insulator transition. It's just the DFT underestimating the gap kind of a thing. Right? So then people then say, okay, look, I think you should update the eigenvalues and not the wave functions are roughly okay, but this is not okay. So so then because it's very expensive to do everything self-consistent. So that's the reason why people will do a whole bunch of things.
Does it help to do some kind of scissor operator?
You can do scissor operator as well, but then you need to decide which state goes up, which goes down. Then you need overlaps, as because I think it becomes something like this, right? At the gamma point, I think you get something like this, and you need to know which one to take up, which one to take down. So so opening up a gap is the right thing to do, and GW will open the gap, but you have to be a bit more.
Your starting has to have some, the gap slightly open.
Right. I mean, it doesn't. You can say, I will do whatever I can, and let's see what happens, right? And it will probably end up in the right spot, right? But it's very. But if you were very strict about it, and you would say, wait, I had a metal. Why should I open? A metal should work very well within DFT, and it should stay a metal within GW as well. Then things get a little bit haywire, and to do things.
It's the semiconductor.
That's right. So then it's okay to open a gap either which way.
No, you need to open up a gap first.
You don't need to open up a gap. What happens is because it happens in only a very small region of the thing, it works out okay. It works out okay because the first iteration already opens a gap, and then it becomes an insulator and everything. But there's a little bit of ghamla over there. So that is what. So the point is that then people start worrying about all of these kinds of things, and so you might say, okay, germanium, okay, fine, I don't work on germanium. Why do I care? Right? A lot of you work on topological insulators, bismuth selenide, things like where the gaps are really, really small, right? And then, you get very, very nervous because, sometimes you'll get a metal, sometimes you'll get semi-metals. All these kind of things can happen. And you really have to be very careful when you're doing this, that you're doing this correctly, that documents are provided correctly and whatnot. Okay. So that was all about GW. The next thing I wanted to talk about was the other part of my talk, which was related to optical absorption. So for a little while, there'll be no technical stuff again. So here's the thing, right? If you think about optical absorption, as I said, at a given point in time, right, your system has both an electron and a hole present, right? So if you, for example, say that, look, I shine a photon comes in, and I have this whole thing is my system. I'm just showing a small region of it, showing that my electron and hole were created, not that my electron and hole were kicked out of the system. I'm just saying that I have an electron and hole present in the system, and they were created at a given point in time. The question that that one is asking is that are these quasi-electron and quasi-hole talking to each other or not, or are they independent particles? Right? And what I tried to convince you before was that these actually do talk to each other, and that makes a big difference to your absorption spectrum. If you said, I don't care, I think they are independent, and let's see how bad do I really do. If you want to do this calculation, you actually just calculate the dipole matrix element between the state with one quasi-electron and one quasi-hole, and the ground state, and you will get a, using Fermi's golden rule, you'll get an epsilon 2 or the dielectric function, which will look like something like this. Okay? This is something that you would have seen. I mean, this is just the Fermi's golden rule applied to a state where you have one quasi-electron and one hole and the ground state. So between that, you have a dipole operator, and that is what you will get. But really, actually, what really is happening is that when you shine light on the system, you actually create a quasi-electron and quasi-hole. But actually, that's not what you create. You actually take the system to a new state, the excited state, and that excited state is a system with one exciton present in the system. It's the first neutral excitation of the system. Let me say that again. It is the first neutral excitation of the system. Okay? And really, that state is really a correlated electron hole state in a solid. It is not just one single slated determinant. It's not at this key point the electron went from here and occupied the state. But rather, once you do this, the system has to actually minimize its energy and figure out what the best possible state of the system is. So I take one electron up. That's not where I end up. I basically have to minimize the energy, and basically that changes the overall excitation energy. So really what happens effectively is that my state is not just one electron hole pair excitation, but a linear combination of a large number of electron hole pair excitations. I mean, it's still normalized to one, okay? But the state is just it's not one electron hole pair, but actually at different Ks, the electron hole excitations talk to each other and find out what the best ground state, what the best excited state of the system is. Okay. So the question then becomes, and then of course you can write the dielectric function based on the ground state and this excitation state and the dipole matrix element between them, and this is what will give you your epsilon. Right? So remember, the difference between this and this is that I have assumed S to be just a product of this two states in this particular case, right? But here I have to actually find out what this S is to begin with and what the corresponding excitation energy is. Okay. So the way you do this, the way you find this this excitation energy is by using what is known as the Bezier-Salpeter equation. So what is the basic idea? So if I take the excited state, I can basically write it as a linear combination of several electron hole pair states in the system. Right? It's not just one electron. So I am, for example, I create a quasi-electron and a quasi-hole in the system. Right? This is a hole creation operator. This is the electron creation operator, right? Or other way around. Doesn't it? B should be the hole creation. This should be the electron creation operator. So I have created an electron and hole in the system at some point, right? Or at some k, if you wish, right? Then I created at some other k, and some other k, and some other k. I have all these, if you wish, single-state determinants, right? And what I'm supposed to do is I have to find some linear combination of this, which will sort of give me the correct excitation energy of the system, which will minimize the energy of the system when I create this. Okay. So for this, what Hans Bethe and I guess Peter came up with this equation. Yeah. Yeah. No. So in which basis are you talking about? See, so if you for a given k, so this is what it is, right? So V is nk and C is n prime k, right? N prime k. So my photon is not going to generate when I shine a photon on the system. I cannot kick out an electron from k to k plus large q, right? It has to be k and k because photon has no momentum, right? So it's virtually vertical excitation, right? But what I'm saying is that what the correct state of the system is not just at 1k I created the electron hole pair, but rather a linear combination of all possible electron hole pairs in the system. These can be written as state determinants because these are all at a given k. At a given k, I can write it as a state determinant. Yeah. So what I can do then is I can actually look at this Bethe-Salpeter equation and actually see what is it that is different about this than simply quasi-particle. So for example, you look at this equation and you say, okay, look, if there were no electron-hole interaction, right, then what happens? I have an independent electron and a hole, right? So what should be the energy differences that I get? Just the difference between the electron energy and the hole energy. That's all, nothing else, right? And that is this first term, this diagonal term of the Hamilton. But now what is happening is that an electron-hole pair, which is generated at some k point, and a different electron-hole pair, which is generated at another k point, they actually talk to each other. So what happens is that my VC, which is which has k in it, so VC and V prime C prime are talking to each other via some interaction between these electron-hole pairs. Is this making any sense or no? So the interaction I will talk about in a second. I don't know who asked the question. The interaction is not pure Coulomb interaction. I will talk about it in the next slide. The electron-hole kernel I will talk about in the next slide. But the idea is that there is an interaction between them. And if I take this interaction into account, my eigenstates are not just a simple vertical excitation. So this is basically the idea. The idea is that if I were to just take, when I say that there is no electron-hole interaction, right? Then my eigenstate is just a vertical excitation from some V to some C at a particular T. But if I put in the electron-hole interaction, right, then a whole bunch of states mix together to give me the eigenstate, right? So I have to actually construct this electron-hole interaction matrix, and on the diagonal of this matrix are just my quasi-particle energy differences.
So what are the other elements in that matrix? The K electron-hole interaction kernel.
So I will talk about what that kernel is in the next section. Yeah? Is that what you're asking? No, you are asking something else. What are you asking?
So you told the diagonal and half diagonal element in the K.
So the diagonal elements are just the energy differences, quasi-particle energy differences, right? So because what I said is, the independent answer is that I created a quasi-electron and a quasi-hole. Right? But now if I make them interact, then these two states are going to talk to all the other states that exist via the interaction kernel, right? Which I will describe in a second. And that's essentially all that we're taking into account. Yeah? So the whole matrix has to be diagonalized then to actually get the answer. So what is this electron-hole interaction that we are talking about? Essentially, what you can show, and you can derive this formally, is that this can be written as the functional derivative of the self-energy and the Hartree energy with respect to the one electron Green's function. Okay? Diagrammatically, what it becomes is that I have this electron and I have this hole propagating in time. And, they do something here. They talk to each other over here. And what this talking over here is that I have an exchange interaction and I have a direct interaction. So basically, think of it in a very simple way. If I have an electron going and a hole going, right? If one is positively charged and the other is negatively charged, then what would be the interaction between them? It will be an attractive interaction, right? It will be just E square over R. But since we are inside a solid, it would not be E square over R, it will be E square over epsilon R. Right? So that is the direct interaction. But not just that, there's also an exchange interaction. So you can actually derive this, and this is what it comes about. So the point is, what we are supposed to do is we are supposed to construct this VSE Hamiltonian and diagonalize this Hamiltonian. And when you diagonalize, the eigenvalues correspond to the excitation energies. And once you have the eigenvectors, you can actually compute from the epsilon 2, you can compute your absorption spectrum. Yeah. So you can also think of this in a very simple-minded way of saying that the diagonal term where there were two quasi-particles which were free, so to say, is like the kinetic energy, and this is like the potential energy, if you wish. Some sense, because it's on the diagonal and one is off diagonal. Yeah, but in any case, the problem that happens here is that the Hamiltonian that you get from here, everything is being done. So far you have the quasi-particle energies which were gotten just from the mean field equation. This also is just building on top of that, right? Everything is, again, the same ingredients are going in. The Hamiltonian from here is very large and it's a non-Hermitian matrix. So if you write it out, you actually have to solve Dyson-like equation for this as well. You have to use some approximations to simplify this. Okay? The typical approximation is that you say that the excitation process and there's a de-excitation process, right? I can create I can shine a photon and create an electron hole pair, or I can de-excite, namely that an electron hole pair can de-excite and give a photon. These two, in principle, can quantum mechanically talk to each other, right? They can be off diagonal matrix elements between them. We usually assume that there is no such interaction. They're very well separated in energy. You assume some static screening, so the epsilon that goes in is static. There are some very good reasons why you can assume that is the case. You use all of that and you actually construct a Hermitian eigenvalue problem, because that we know how to solve very easily. I mean, we also know how to solve non-Hermitian eigenvalue problems, but then interpretations become a little bit.
How did the non-Hermitian come?
So actually, it comes about because I didn't show the full two-particle. So there's actually Dyson-like equation that comes in. So there's an L, which is the two-particle propagator, and then it becomes an L naught, which is the independent propagator, plus the kernel comes in L naught K E H L, and that is actually what leads to. That's the real equation that you have to solve, just like the quasi-particle equation, right? The quasi-particle equation is also non-Hermitian, right? Because the spectral weight under the quasi-particle is not 1, right? So the particle is, you're losing some particle somewhere. Right? So the same way, this is also non-Hermitian in that sense, because there's a lifetime to this exciton as well. Sounds like, because you can actually you can annihilate this exciton because electron and hole can combine. So in that sense, there's a non-hermiticity that comes in. You can get rid of it by assuming that these are good eigenstates and I'm not going to worry about it. That's usually what works. What do these matrix elements look like? So this actually looks a whole lot like what you might expect it to look like. Essentially, what happens is if you write, this is just simply you put W instead of this, and you just write out the matrix element. That's all there is. You put 1 over r minus r prime for this, and you just write out the matrix element, and that's what these look like. How do you compute them? Exactly in the same way that I told you about how GW is computed, you actually have to calculate these electron column matrix elements. These plane wave matrix elements and then. So just to give you a sense for how large these matrices can become. Okay. So we are going to give you an example of silicon. We are not going to solve it in your tutorial because so if you just count the dimension of the matrix, right? So typically you will need a 10 by 10 by 10 K grid, 10 by 10 by 10, right? So that's 1,000 K points, right? Then you need 4 occupied bands, and then you let's say have 4 unoccupied bands. So 4 times 4 times 1,000 is the dimension of the matrix. No?
So how do you decide how many unoccupied? Because you can actually go.
You can actually go to infinity, absolutely, and you should in principle, right? But of course, you're not going to do that. So what?
Is 4 sufficient by?
Yeah. So the way you argue that is the following. So you say that look, I am interested in an energy window. So typically, when an experiment is done on absorption, you will have an energy window. Let's say of a UV vis. So let's say 5 volts or 6 volts. So you say, okay, I'll start with my energy window of 5 volts, and all transitions which are within 5 volts, I will keep, right? And then I'll keep some just for good measure on one side and the other side, and that's all there is. So you'll typically go, let's say instead of typically I'll show you, for example, this spectrum I'm showing you is up to 10 volts, right? So silicon, the valence band manifold is what 12 volts, right? So you can go 12 volts above, and that includes 4, 5, 6, 8, 10, something like that.
Yeah, my question more than the optical absorption. If I'm, for example, focused on just the band gap of silicon, and just to reproduce the masses,
the effective masses of from the GW or the
from the GW.
So that is a much more complicated question because there is no such argument that can be applied.
Yes, exactly.
So there you have to actually converge the answer, which of course means which means that you just do it till your computer says, till you say that I can't do it anymore, and then you try to extrapolate. So there are actually some techniques. I shouldn't just say that. So as you might know that for the static limit, there's an analytic answer, right? Because you can actually sum over infinite number of times. So what you say is that the difference between the analytic answer from static and the sum over states answer up to that for the static, that difference can be used to estimate the correction to the GP.
Usually we should check the peak is shifting or not by increasing the number of unoccupied.
Correct.
That's
also, but she's talking about the GW.
In GW also, you can plot the peak and you can check whether the peak is shifting or not.
You mean the peak of the spectral function?
Yeah,
yeah, you can do that. Yeah.
But that's like your convergence, I think we're saying.
Right.
Yes.
Right. Yeah. But the simpler solution is usually, so the static remainder actually is modified static remainder as we call it. There's a factor of 1/2 that comes in, which Professor White to figure out why it should be 1/2. I mean, that difference should be. But anyway, so that actually works out reasonably well. But there's also a sum over states in the epsilon, which I don't know how to do any extrapolation. So since we are in the last 5-10 minutes of the talk, let me just start out. Let me just show you why we were doing all of this, why we went through all of this to begin with. Again, the idea was that if you do GW, then you actually end up with the theoretical gap versus experimental gap in very good agreement for a large variety of materials, right? But I hope I have also convinced you that doing GW is hopefully worthwhile. B, it is going to be expensive, and there are a lot more convergence parameters than in your DFT. You have to converge your calculation correctly, and and so on. Similarly, for the Bethe-Salpeter equation, which I talked a little bit less about, you actually, if you do this correctly, you actually can reproduce a large number of features. I mean, excitonic features at least in the spectrum very well. Now, just a few words about the codes, GW, BSE codes. I don't know whether BSE is implemented in all of these. But in the standard packages that you will find today, a large fraction of them already have GW implemented, right? At least some versions of it, right? In fact, most codes are actually moving towards more and more GW BSC implementation.
Not for the periodic stuff.
Not all of them will not have for periodic stuff. That is correct. I mean, for example, this is only for molecules. I think these are all for periodic systems. ELK is also, I think FHIMs and ELK also have for periodic systems. Okay.
Convergence issues.
Okay, so that is of course, depending on the basis sets, the number of parameters. I have told you. I mean, I hope I've told you that there are a lot of convergence parameters, right? Basis set convergence is another parameter that you have to add to that list if you actually are not working in plain text. And it's difficult to converge these, but people are now beginning to routinely do these calculations, especially for simple systems, and it is something which is within the grasp of this kind of things. I have to show this. I am a developer. I used to be a developer in this code, and this is what we're going to use for the tutorial today. It's called GW. We're going to use this as a tutorial because I know it well. That's the only reason why. I don't think there's any difference between YAML's implementation, WASP's implementation, Abinet's implementation, and so on. But you should try to see whichever one. So if you are very familiar with the code, DFT code that you use routinely, then try to see if there's a equivalent implementation in that code, and usually they have a very nice tight integration and so on. Here is a set of references. These are I'll be done. These are I have taken, I think, from all of these something or the other. I think this should be the starting point of learning about DFT, about GW and BSC. So if this is something that you're interested in, this would be the first place I would go to. These are the references I would go to. Yeah. That's it. I will leave this presentation here, and I don't know if this can be distributed to everybody if they want. I have also derived the GW method using Schwinger's functional derivative method here. I don't think I will go over it. I will just leave it up. I will just leave the floor open to questions.
So we have 3 questions from the online.
Yes.
From Dhani, for calculating chi, you mentioned we only need the eigenvalues and eigenfunctions from DFT.
Yes.
However, in DFT, only occupied states have meaning. How do we get the eigenfunctions and eigenvalues for the unoccupied states, which have no physical meaning in DFT? By chi, I mean polarizability.
Yes. So what you're saying is correct, that indeed the unoccupied states don't have any physical meaning. But what we really need are eigenstates for constructing the Green's function, the DFT Green's function. So even though they may not have physical meaning of any, because they don't correspond to any density and so on, the Green's function can still be constructed by a sum over states. You can also construct, for example, the Green's function by h minus e and times g is identity. I mean, you can invert that equation, which would essentially lead to this kind of an expression, as I have written here. So in that sense, we use the unoccupied states. Okay.
From Shivalika Sharma, is quasi-particle renormalization factor is relatable to the effective mass?
I think in Fermi liquid theory, this is related, right? I think it is related in Fermi liquid theory, but I don't think it is related to the band mass in the normal sense. But I think in Fermi liquid theory, there's a connection between that and the effective mass. Yes.
From Showman to Doctor, LDA underestimates the band gap magnitude, while GW calculation improves it. Question is, what happens to the position of the band gap center? Is it the same in either cases or not?
No, it is not the same. In fact, so yeah, it is not guaranteed. Okay, so let me put this. It can of course remain the same. It doesn't have to remain the same, and a priori there's no way of saying that it will remain the same. So because the valence band, so the way it remains the same, the center of is that if the valence band and the conduction bands move by the same amount, in which case you actually know how you have to do only one calculation and not two. but that's not the case. You actually have to do both the calculations for the valence and for the
Another one from Debashish. Should we expect an excitation of the exciton in the excitation spectrum for a metal?
Metals will also have excitons. That is correct. Because dielectric screen, metals have as Q tends to 0, the dielectric function diverges. So you might think that everything will be screened out, but that is not the case, because when you look at things which are farther away in a metal, they actually behave a lot like semiconductors. I mean, if you look at the Q tending to 0 region, a metal and a semiconductor, the screening looks more or less the same. So indeed, you will see excitons in a metal as well. One place which is an example of seeing excitons in metals is in carbon nanotubes. There are metallic nanotubes which actually have excitons, which have excitonic spectra, which is where the peaks are.
So, are there examples for overestimation of band gaps in GW?
Examples of overestimation. Yeah, I'm pretty sure there are. Even in my I need to look at that.
And why so?
Because screening is not right. I mean, that's a simple answer, but I don't know. When we do GW, it's a question of what GW are you doing first of all, right? Is it the G naught W naught, or is it self-consistent GW, and so on, right?
Yeah, suppose we are doing eigenvalue GW.
So what happens is the following. So if you assume that the quasi-particle wave functions are the same as the DFT wave functions, right? So epsilon has to have some rules, right? So when you just replace the eigenvalues by the DFT eigenvalues by the GW eigenvalues, you can show that if one satisfies the sum rule, the other will not, right? So you mess around with things when you do it in this way, and your screening can become slightly incorrect, and it can lead to overestimation. In fact, what you will find is that self-consistent GW, people often find that it overestimates. Okay. But the way it overestimates is not going to be so bad. For example, if you look at this LDA estimate, I mean, this is 14 electron volts, right? This is a very large scale. You will find that on that scale, this will be just slightly above this. So it overestimates, but it systematically overestimates, right? So you can ask, so how do you fix that? In principle, this is an approximation. We did several firsts, I told you. The first diagram, the first order, and then linearization, and so on and so forth. If you remove this, there's always the vertex, right? The vertex is not included in all of this. You have to actually go back and. So
this, if there are any overestimation, does it affect binding energy of exciton?
Overestimation of the quasi-particle gaps.
Yes.
So binding energy is with respect to the quasi-particle edge, right? I mean, the definition of the binding energy is from the quasi-particle. So basically, if you look here, the quasi-particle. So this can be off. This difference can be off, right? But this binding energy is usually is from the quasi-particle edge. So the definition of the exciton binding energy is the optical gap. Sorry, the quasi-particle gap minus the optical gap. That's the definition of the quasi-particle.
So that is my question. Is it possible that optical gap also shifted accordingly?
Yeah, that's if you add a constant over here, the whole thing will shift. Yes.
Yeah. So one last question.
Yeah.
So how does this theory work well for strongly correlated system? Suppose we have ferromagnetic system.
So strongly correlated is going to be things like Mott insulators and
okay, suppose for magnetic system.
Magnetic systems, you can generalize this and do the theory for that. Strongly correlated is, for example, in a Hubbard-like system, right, where you have flat bands, where the first term in the diagram is actually the first diagram is not sufficient to capture the electron correlation.
So how U is it?
So this is
tailored in.
So because it is GB, so in the strongly correlated system, you are actually replacing the V by a U, right? That's the way to think of a strong. I mean, that the Coulomb interaction is on site, and you replace the bare Coulomb interaction by this U parameter, right? That's usually the way to think of it. So in that case, there are other diagrams which are more important than the first diagram that you are actually. So Hartree-Fock, of course, is very important. right? And this is like a screen version of our box. So you start out with that. So that's not going to say that this is not important. But what I'm saying is to get the exact numbers right, you need to include all the other diagrams as well. So people have done, for example, GW on a Hubbard Hamiltonian, right? And they find for U by T of the order of 1 or 2, it usually is rough. It matches, in terms of some properties with the exact answer numerically. But then if you go beyond that, a lot of physics, for example, mod physics in the large U limit, this doesn't happen.
To add on an clarification, but you do have these other terms which are not there in the GW, etc. Those kind of other Feynman diagrams.
Yes, absolutely. That's precisely what I'm saying. Yeah.
No, I mean, it's like you showed this morning certain higher order ones.
Yeah.
But there's also a class of Feynman diagrams which are not included within this. It's not this higher order GW.
So, but GW in principle, if you're counting diagrams by GW, then the counting is exact.
So, I mean, these are one set of diagrams, but like you have 2 electrons coming and scattering out.
Yes.
So those kind of diagrams are not there in this.
Right, but what happens is eventually this is a 1 electron Green's function that you're calculating, right? So for this 1 electron Green's function, you can actually scatter, for example, a plasma, right? Which is, this is like, I mean, if you talk to people who do mod physics, they will say that this diagram is essential for in mod experience.
You have those two, I mean, you can draw it.
Yeah, absolutely.
For instance, I was just thinking of these kind of diagrams where you have 2 electrons coming in, they interact, and then they go out.
Like in the BSc.
Okay.
Like in the BSc. But the thing is,
but
this is a 1 electron problem, right? So now you're looking at the 1 electron propagator.
2 electrons coming in, and this is a Coulomb interaction and scattering and these kind of things.
Agreed. What you're saying is I agree with that. But what I'm saying is we are calculating the self energy for the 1 electron Green's function, right? So at the end of the day, I have to have a one electron in and 1 electron out, right? I mean, I have to have. So I can of course couple this to, let's say, this thing and then make it talk in some way.
These are like not.
Right.
You're bringing in 2 electrons.
Right. It is that you have 1 electron propagating and it talks to, for example, an excitation in the system which involves these kind of things or a plasmon or so on and so forth and everything in between. So that, in principle, this diagrammatic perturbation theory is exact, right?
I mean, I'm like, okay.
That's what I meant. That's what I'm trying to say. But it is. In principle, you should see poles over there as well, because if it is related to this, then these will scatter and you should get broadening from here. And in principle, everything should be there. But in practice, of course, you only do the first diagram. So
For instance, people do GW plus, say, DMFT.
Right.
So that is to grab like the electron.
No, so what typically when people do GW plus DMF is that in some part of the Hilbert space, they will not do GW. And they will say, here, I will solve my stuff exactly, right? And the rest of it, I will figure out how to couple it to the rest. That is the other part, right? So I do DMFT in this subspace, in this Hilbert part of the Hilbert space. I will do GW for the rest of the Hilbert space, and then couple them together and try to not double count anything, right? Because if I did GW everywhere, then I've counted this interaction in some way. And then when I do it again with the higher order theory, then I have to subtract this part out and then count that part. So that is usually how the extended DMFT and the Zilke and stuff and all of that. I think they couple it in this way. That they make sure that some part is, nothing is double counted, but GW takes care of the long range part, and DMFT takes care of the short range part. That's very easy to say, but coupling these is, the equations become nightmarish. So, but yeah, they have figured out a way. And I think extended DMFT also does something along those lines. Yeah.
Sir, for some time result experiments,
Yeah.
we are not including the dynamical part of the Green's function.
So sorry, say that again. Further?
We are not including the dynamical part in the Green's function because you say the frequency is tending to 0 or exactly 0.
In the Benesov
Time evolving processes, we are not taking into account the Green's function.
I didn't talk about. I don't know what you're saying.
I am telling that the Green's function which you mentioned before, we are omitting the frequency part. Means we are
No,
not.
we are no, we are not supposed to omit the frequency part. Sometimes, when we, for example, doing the Bethe-Salpeter equation, we can omit the frequency part and we can get a reasonable answer. That's all I'm saying. There's no, I mean, there's a formal stuff which is written out. It is a function of t minus t prime. There's nothing you can do about that. It turns out that it doesn't vary very strongly and it is the same as t minus t prime equal to 0. Then you can do something about it and get it. But in principle, you're supposed to carry everything, right? Yeah. So in reality, I mean, reality doesn't care, but we can only do so many times. Yeah.
Any further question? If not, then let's thank the speaker. Break for tea, and we come back at 3:45.
I mean, I want copy or something. I just done something for. I mean, not first.